Yeah, so it was differential equations, geometry, and arithmetic. I guess today will be a little bit more also geometry coming into the game, and I will talk about the theorem about diagonals, in fact, but for which mixed Hodge theory is needed for its proof. So I will try to be as non-technical as possible, but I first have some loose ends of the last time, which I think would be good to bring to a fixed end. So I was discussing operators written in the theta form. So this would be an hypergeometric operator where P0 and P1 are polynomials, but you can go on. And this is the form I prefer to write things, because it gives an easy analysis of the differential behavior at 0 and in infinity. So you can read off many things easily. So now 0, so theta is the logarithmic derivative, so the points t is 0 and t is infinity are distinguished with a fixed point of this vector field, if you wish. So if you write a solution to that in a power series, so then I mentioned last time that this immediately translates into a recursion of this sort. So, but if you start summing at 0, or let's put it, if we start summing over n's which are positive, then if for n is 0, all these coefficients are 0. The earlier coefficients are 0, showing that the P0 must be vanishing for that. So if all the ANs are 0 before an index n, then P0 of n must be 0. So you get a solution if you, so let's, if you want to have a solution which starts with t to the power n, you want all the earliest to be 0, then you better have P0 of n is 0. So you can start a power series. Huh? You can start a power series only if this term is 0. And now, in fact, I didn't say that n is an integer. N could be also a fractional power series. So if you have a series which are, maybe better write it like this. But of course, then the conclusion is exactly the same. So it means that this alpha, the exponents of the first term, must be a root of the polynomial P0. That's why this polynomial P0 is called the indicial equation. And the roots of the indicial equation are the starting points of such series. Maybe this was not explained clearly enough. And now, if you get a repeated root, then what do you get? This is a trick you can find already in Euler, which was used with great success by Frobenius. Then you differentiate this series with respect to alpha. So multiple roots of the polynomial P phi to differentiate your expression with respect to alpha. So you infinitesimally move alpha, and if you differentiate this with respect to alpha, this is of course log t times alpha. So this is just t times t to the power alpha. By differentiating such an expression with respect to the index, you create the logarithm. And well, Euler uses this type of things of the logarithm as the t to the alpha, where alpha is infinitesimally small. Of course, in Euler, there are so many things, and it's not so clear. But it's always said, read the masters, read Euler, because that's where the 19th century mathematicians got many of their ideas. So we have this slit disk, and we want to write solutions. So now I want to take the model equation where the polynomial has a root alpha, but say of order k, and we want the solutions to this equation. So we just take the simplest case where there are no terms p1, p2, etc. Just the first. So this is my p0 alpha, p0 of theta. And it has one root alpha of multiplicity k. So what are the solutions to that differential equation? And well, if k is 1, then phi is 0. And phi is, of course, t to the power alpha, is a solution. But now, if you take log t times t to the power alpha and apply this operator, so you get theta log t times t to the power alpha plus log t times theta t to the power alpha minus alpha times t. And the theta of log t, so you differentiate with respect to t, so you get 1 over t, but then you multiply by t, so this is 1. And you get t to the power alpha minus here alpha, and here this is alpha times t to the power alpha, so these two cancel, so this is t to the power alpha. So if you apply this operator to this one, you get just the previous one. And so you get theta minus alpha squared of log t is 0. And so the solution space on this operator on the split disk is just a vector space spanned by these two functions. Huh? Log t, yes. So this is of course there is much more to say about all this finesses of the expansion, but this is the main idea. If you have a theta, a root of multiplicity k, you will expect log to the power k. But in exceptional cases, it is not you don't get log. You get not all powers of logarithms necessarily. Now you can analyze the local monodromy of the solutions. So you have the solutions which will be power series in logarithms and the fractional power series. So what you do is you have the slit disk and you take some point and you start analytically continuing. And if you do this, you run with your value t, you run around the origin with an angle phi, which runs in 0 to pi. And the result of doing this will be, in the end, where you get sort of 2 pi I times t. So the process of analytically continuing and coming back is formally, you can see by substituting t by e to the power 2 pi I times t, which is of course sort of silly because this is 1. But the idea is you let phi increase from 0 to 2 pi. And so if you do this monodromy transformation t to the power alpha, and you replace t by this, so you get e to the power 2 pi I alpha by t. In the monodromy of log, you get, of course, log t plus 2 pi I. If you log replace t by e to the power 2 pi I times t, you get this. And therefore, you see, you can write down the matrix. If you take this operator L and the local monodromy around 0, then you have to also compute t. The monodromy of this, you do both at the same time. Of course, you get a diagonal part, 2 pi I alpha, 2 pi I alpha. And then the logarithms create a Jordan block, so you get 2 pi I. So these exponents, they are logarithms of the eigenvalues of the local monodromy, and the logarithms gives Jordan blocks of the local monodromy. This is a local monodromy along path gamma encircling the origin. So from the differential operator itself, from the initial equation or the analysis of the solutions at the singularity, you can find the local monodromies algebraically. And if you do it for this operator, the Legendre differential operator, which has this solution f some everybody's best friend, then yeah, this is a hypergeometric operator. There are 3 singularities, 0, 1, and sort of infinity. Now to get the monodromy, the total monodromy, so the local monodromy around this point will be a Jordan block. So here you get a repeated root 0. Alpha is 0. So you get just a Jordan block here. You get a simple Jordan block up to a linear transformation of this matrix. The monodromy here, from the geometry, it's clear that what is happening at here is the same what is happening here. The local monodromy is here. Again, a matrix conjugate to this Jordan block matrix. And now, if you look at the exponent at infinity, the exponents are are a half. So the roots of the last part are the exponent at infinity with a minus sign. So the exponents are a half. And e to the power 2 pi I times a half is -1. So the eigenvalues of the monodromy are -1 here. And so here the matrix is conjugate to -1, 0, -1. And here 1. Or you can write 2 pi I if you like. But these matrices are all conjugate. So locally, you have at 3 points you have a Jordan block, and monodromy, global monodromies, going here. So this is T, the monodromy around 0. So the base point is say a half, and you have here the monodromy about 1 and the monodromy about infinity. The product of these three matrices is 1. And now what rigidity means is that if you know the local Jordan structure, there is only one, up to conjugacy, one solution for these matrices satisfying this condition. So if you have the loop around infinity, which is of course, this is the inverse of the composite of these two loops. So you have two Jordan blocks with eigenvalues 1, and the product must be a Jordan block of eigenvalue -1. There is only one triple of such matrices up to conjugacy, and it's an exercise to find them. In fact, the geometry of the situation, because this was obtained from this elliptic curve ET, you can see what happens to the cycles. Cycles on the Riemann surface. This is the cycle delta. This is the cycle gamma. And if you now do the monodromy with T, you walk around the origin. You move this point here around this. Then you have to see what is the action of on the H1 of the elliptic curve, which is spanned by these two cycles. And this is an exercise in topology, and I think the majority of the audience is more on algebra, so we're not going to this exercise. But there is one person here, Erik, who can do this. And he has written very useful routines to get a hold on the monodromy. And one uses explicit analytic continuation. And maybe we find a possibility that you illustrate your program, because I think it would be quite instructive if you can analyze this example with, so we relegate this to the exercise. Okay, now I'm getting out of time. Okay, so so there were lots of classes of differential equations or power series mentioned in the previous lecture, and I want to introduce the class of differential equations of geometrical type or geometrical origin, which are factors of Picard-Fuchs equations. Picard-Fuchs equations share all the marvelous properties that were conjectured on the previous talk. There is a Frobenius structure, and everything is as good as possible, I think, if you are a geometrical situation. So this is Picard-Fuchs. And then I will So if we have x is a variety, so it's something like elliptic curve given by explicit equations. But it may be more equations, and they depend on the parameter. And well, I will always assume that these are defined over Q. So these Fi's are polynomials with coefficients in Q. In T. Like we had there, even the coefficients were in Z. If you can clear denominators, you get coefficients in Z. But this is a variety, and it may be in affine space, it might be in projective space, it doesn't matter too much. Then we can look at the end homology group. This is the group of n cycles. So the dimension of x would be d. And you can look at the de Rham cohomology group, which is, in fact, can be seen, you take the algebraic differential forms on your variety. This is a Q vector space. You take the closed forms modulo the exact forms. So this is the end Rham homology groups. X. And then we can integrate. We have an omega here and a gamma here. We can integrate the differential form. And if x depends on t was already here. So everything now depends on t. And I get a function, phi t. This is a period function. And this period function satisfies the differential equation. It's very much just a generalization of the elliptic curve we have. So this satisfies a linear differential equation. And why is that? Well, this de Rham cohomology and the ordinary homology are sort of dual to each other, and this is a finite dimensional vector space. Well, the choice of x, yes. Yeah, well, this does not depend on the choice of delta. For each cycle, it is the same equation. Delta, the omega, a fixed omega. If you take another omega, you get a different differential equation. If you integrate over another cycle, you get the same differential equation. The reason is that you can integrate, differentiate below the integral sign. So this is in highbrow mathematics the Gauss-Manin connection acting on the Rham cohomology. But just think of what you do here with the elliptic curve. We have an integral, say from 0 to 1 dx. You differentiate this, and you just differentiate this rational function, or this algebraic function. If the Rham cohomology is finite dimensional, then among the forms omega, nabla omega, these are all in is the wrong group. And this is finite dimensional, so there must be a relation between the omega and the derivatives of omega, and that translates into a linear differential equation. So there is an L, AI, such that L and this L is independent of the cycle you choose. So, and this is L is called Picard-Fuchs equation. Operator. This can be, I did not say how it really depended on T, but maybe we say we have a family over P1, parameterized by P1, and xt is a special fiber over the point T. And then you can, from this, you can consider this as a variety over this field. The polynomials are over Q. You can consider it as a variety over that field, and the computations being taken place over Qt. And then this is really a rational function ddt. So it's a linear differential operator with coefficients which are rational functions in T. This is Picard-Fuchs equation, and this is a basic invariant of the geometry of the family. And these operators have very special properties. I want to make a few such LDEs of Picard-Fuchs type have very special properties. First of all, you have this family of varieties. This homology group is really a lattice. So this is a z to the power something. So it's a lattice. And this means that the monodromy representation is conjugate to an integral. So here we take out this set of singularities. So you have a family of varieties. There might be singularities. So now you see it is becoming geometry. So sort of. So these are the singularities of the family. It can be almost anything. And the fundamental group of the complement of the singular fibers, these points, it is a linear transformation on the cohomology, but also on the homology. And it means that the monodromy matrices in an appropriate basis take values in integral matrices. In particular, the local monodromies are given by integral matrices, and that means that the roots of the initial equation are algebraic, because they have a characteristic polynomial with integer coefficients. But in fact, the exponents are rational. This is deeper, but true. Yeah. Was there an N? No, N. N is the dimension, say. No, it's not necessary, but you can restrict to that case. We will do in a minute. Oh, the second property is the so-called monodromy theorem. Saying that the local monodromies are quasi-unipotent. And there is an exponent, so that if you take the local monodromy C to that power, then it's unipotent. So if you subtract the unit matrix, it becomes nilpotent. And in fact, the nilpotency is n plus 1. So it's an n cross n matrix. It's d plus 1. So d is the dimension x. So if the dimension is 1, you have a family. So the exponents are rational. And we have a bound on the size of the Jordan blocks. So if you have the D is 0, if you have a family of zero-dimensional varieties, then you have the T line, and then for each value of T, you have finitely many solutions. So you really have the situation of a covering space, or X is the graph of an algebraic function. So X is a curve defined by an algebraic function in T. So here's the variable T. And then this theorem tells you there are no Jordan blocks. Monodromy will be finite. If you go around this point, you get a substitution of the permutation of the leaves of the covering. This is in preserve. Yeah. The fact, no, there are several proofs. Right? There are many.
But it's not immediate.
No, it's not immediate. One, okay, but the consequences are noteworthy. So if you have a covering, the local monodromies are finite. It's a permutation. That we're basically in the situation of Puiseux's analysis of an algebraic function as a covering of P1 and the substitutions. And then for D is 1, we have say, a family of curves. Say elliptic curves, and then like the Legendre family of elliptic curves with singular fibers. And now the statement is there can be only Jordan blocks of size 2. For the elliptic curve case, it's clear because the cohomology is two-dimensional. But now imagine that you have a family of curves of higher genus. Cohomology is much bigger, but still the Jordan blocks have maximal size 2. There cannot be a log squared. So here, no logs. What was no log squared? Because, yeah. M is a common denominator of the exponents. You can say something about it, because if you have a family of elliptic curves, it can be at most 6, I think. There is it's about bounding the order of automorphisms of curves. But that's not the issue here. So the exponents are rational. So one can prove this as a consequence of the theory of Hodge structures. So this is a theorem by Griffiths, proved this way using Hodge structures. There is a proof by Grothendieck. He proved it using arithmetic geometry. And there is a proof by Brieskorn, which is using Duco van Straten theorem, that if you have a number which is algebraic and its logarithm is also algebraic, because we have the differential operator is with rational coefficients, and the exponents are logarithms of the eigenvalues. Then you have it also. Then necessarily the exponents are rational. D is the dimension. Yeah, I should, Gregory was saying, well, maybe we better assume n is D, but it's not necessary. The variety in general has many homology groups, but usually the middle homology group is most interesting, so the HD of a D-dimensional variety. And in fact, to define Picard-Fuchs equation, you could take also D. This is proved in detail in the book by André on G functions. So, and much more precise statements there. So, what other marvels are there? 3, P curvature is nilpotent, for P, sufficiently big P. So here, these equations involve finitely many rational numbers, and if you avoid finitely many terms of bad reduction, then you can show that the P curvature is nilpotent, and this we once treated in a Lisbon conference. And maybe we are going to hear about that, Julian, at some point. If it's 0, then the order of nilpotency is related to this order of the logarithms appearing here. So for a finite algebraic map, you would get nilpotent, the P curves are vanishing. And you're asking for the reverse. And now the fourth, this is what I want to focus on. If the local monodromy around a point, say 0, is unipotent, so all eigenvalues 1 with maximal Jordan block so the order of nilpotency is maximal, so there really appear Jordan blocks of maximal possible size. Then if you write the order differential equation P1. Yeah, then there is a unique solution, holomorphic solution, power series solution, phi t 1 plus qt t. So there is a unique, because here you get a maximal Jordan block of size, so there is only one holomorphic solution. I scale it to have constant term 1, so it's unique with these properties, and the coefficients of the power series will be rational, like in our example where you got is f half half 1, but now the theorem is it and has Eisenstein property. So the Eisenstein property, meaning that there exists an n such that phi n is a power series with integral coefficients. But this is the theorem I want to focus on and explain a bit why it is true. So we, in the example for the elliptic curve, we had phi 16t was, so the series was 2n over n squared 1 over 16. If you replace t by 16t, it is integral. So, yeah.
Minimal.
And? Yeah, yeah.
But it's not minimal for period over when you
right, to choose an omega.
Yes,
You can take another omega. Yes.
but none is minimal.
No, it is, this is the operator killing all the periods. But I'm assuming having a maximal Jordan block. So the,
I
there
mean,
is not,
yeah, when the mean is minimal for the choice of omega and the delta, but this possible minimal over qt.
no, but then the operator is not irreducible.
Yes, that is my question. Maybe
Yeah.
not if it is.
Yeah, but then, okay, so in general, one continues and say it's an operator of geometric origin if it's a factor of the Picard. And then, but for me, for the moment, I didn't want to do that, speak about factors, but you're right. But this was, this, and I just erased it. I'm saying that that function phi t, the holomorphic period, if you have a maximal Jordan block, is always the Eisenstein property. In fact, the theorem of Cristol and André is stronger. It's saying phi t is a diagonal. In fact, so phi t is a of algebraic function. And 2 times by a theorem that any diagonal of an algebraic function can be seen as a diagonal of a rational function in twice the number of variables. Of rational function. So, and I want to explain this remarkable fact. So the phi t is in diag. I don't know how that works then in your diagram, what it implies. We of course know then that the differential equation has a strong Frobenius structure by Cristol. And so let me tell the story of the diagonals.
Not a joint result.
Huh?
It's not a joint result.
No, it is formulated in this book, and it is, he ascribes it to Cristol, but if you see what Cristol shows it only in a special case, which I'm going to present. But if you look at the special case, you understand why it works in general. And then, so I call it this. Oh, and they have a more general statement, but it's more clumsy to formulate. So I took a special case of the story of the diagonals. So can be very brief. It's a famous exchange of letters between a lifelong friendship between Euler and Goldbach, where they write in half Latin and half German. It's very amusing to read. And Euler tells Goldbach about the theorem he has proven, and it's in fact the series, the result which was quoted by Julien. So that the generating series of the Kaplan numbers, and for Euler this is counting triangulations of the n-gon. This is a generalization of enumeration of the different ways to triangulate an n-gon, and it is this algebraic function. And then Goldbach writes to Euler, very nice, how surprising that it is that you have this function and all the coefficients being integers. And then Euler said, well, he had not spent a thought on it, and he said, well, if you take this one, this is also an integral series. So you have a power series, an algebraic function, and you replace t by n squared t, and it makes it integral. So this is just appearing in that exchange. And then the last paper by Eisenstein, briefly before he died, and it's really just a letter to the containing no proof, has this famous theorem. So Eisenstein. If phi t power series starting at 1 if phi is algebraic, then you have the Eisenstein property. This property. So it is sure that Eisenstein knew about these things. Of course, this does not characterize the algebraic functions because the f half 1 or the period functions also have this property, and they are transcendental. They're transcendental series because logarithms appear in the differentially in the monodromy. So, but this is a first result, and then the proof. There is no proof. Eisenstein say it can be proven by the method of the general coefficients. This is all he says. I don't know what he imagined for proof. So, Fürstenberg theorem saying phi t phi is two diagonal, precisely if phi is algebraic. So phi so what is a diagonal? It was already mentioned in the previous talk. So if we have a power series, formal power series in n variables, you can attach to it the diagonal power series of one variable by taking one and then going to the diagonal ak. And I say if you have a rational function, f is p q, and q is non-zero, and p and q are rational, are polynomials, then it can be expanded in a power series and then can be taken its diagonal. And we say phi is n diagonal. By definition, there is an n diagonal of a rational function. So, in fact, if you look at the proof, okay, this can be proven. It's not too difficult, but if you look at it, so proof, there is a inherent geometry in the proof, and it is good to go through this. So we take the mapping from A2 to A1, the plane xy, and map it to x times y, which we call t. So this is, now I want to think geometrically of this. Mapping from the plane to the line, and the fibers is a hyperbola. And for t equals 0, this hyperbola degenerates in these two coordinate axes. And this hyperbola xy equals t, if t is non-zero, then of course x can be eliminated, and y is as t over y, where you can eliminate y as t over x. So this hyperbola is just isomorphic by looking at the x or the y coordinate to C star. And the hyperbola is just a copy of the plane where you remove the origin. Remove the origin. And now there is a cycle here, which is sort of contracted. We have seen this before in our elliptic curve. There was a vanishing cycle. Here there is a vanishing cycle in this simplest case. This is sort of singularity theory. A1 singularity. That cycle here is the cycle here. Now, if you think about the diagonalization process, then the diagonal of a polynomial, a ratio between two polynomials, so can be written as follows. This is f. So if you think of the function f, which is the rational function p over q, and this is a power series in two variables. And now, if you just write down that power series, make this substitution, and then take this Cauchy integral, this is integral to pi I, over this cycle delta, which is the same as the cycle delta here, then this is just this is the diagonal. Because this picks up only the diagonal terms. You have x to the power k times x to the power y is t divided by L, and then you do theta. you pick up only the terms where k is L. This sum. So this is taking the diagonal by an integral. In fact, the diagonalization process is an integral, but you don't want to write the integral if you do algebra. But in geometry, it is just an integral over a vanishing cycle. And now, if you look at this rational function, then here you have this hyperbola, and you have the function q, the denominator. Where are the poles of the function? And look at this function on this hyperbola. Maybe I use color. So what is important is this is q is 0. The rational function, so this is a polynomial in x and y. It's a curve in the plane, and it intersects this hyperbola in certain points. And these points are in the C star. This is the cycle. And then there are certain points here. So this integral here is a sum of residues. These points here are the poles of this function here, and you take a sum of some part of the poles, so this is an algebraic function. You see, this is solving all the roots is the roots of an algebraic equation. You take a subset of roots with weights, so this is an algebraic function. They're the poles of the thing you're taking a diagonal of. So they're the zeros of Q. Yeah, because this hyperbola is the same as C star. So x, y is t. Yeah. Yes. So the x coordinate or the y coordinate. If you write it down algebraically, you must choose. Do I take x or y? And then you have to see the position of the cycle. Some roots fall in the cycle and some fall outside the cycle. And yeah. This is the you're right. This is the usual schizophrenia you must like if you're a geometer. Okay. There is also the converse theorem, which is so if you have a diagonal, if a two diagonal is algebraic, but if you have an algebraic function, you can write it in an explicit way as a two diagonal. I will omit this here, and I will maybe make an exercise of it. To hurry up. Well, let me say, of course, a diagonal has the Eisenstein property. This is already mentioned. This is easy to show. But another thing is on remark. What you often have is a Laurent polynomial. Yeah. Yeah. Phi t is algebraic function because it's so each of these roots is an algebraic number depending on t, and it's just a sum of weighted sum. It's a crazy proof, but this is the proof in Furstenberg's paper. I think it's very elegant. It is in his paper. Yeah. So let me say a big source of examples of diagonals are Laurent polynomials. And you take the nth power of a Laurent polynomial and take the constant term of nth power. We did this, I illustrated this with this is correct. This is correct. So you can write the binomial coefficient as just x plus 1 over x. This is the square. And now for each Laurent polynomial, you can, this constant term is the same as the constant term series is then phi t defined as this series, generating of the constant terms. This is a special case. This can be written as a diagonal. It is the, now it's m. So it is the m plus 1 diagonal of your Laurent polynomial multiplied by x1 up to xn, and then the last variable, m plus first variable. You take the m plus 1 diagonal of this one, you end up with this. So this gives a way of doing, writing the, yeah, there are easy ways, but this is so in fact, there is I have to I will now describe to you an even more complicated way of writing it as a diagonal, the same thing, but which has the property that you understand that it holds, that can be generalized. So this is periods diagonals. I see I'm running out of time. So this is Christol. So he takes again the elliptic curve, Legendre normal form, but there is one sign is flipped here. So this is for t is 0. It is a curve which has a node. And now what you see in the neighborhood of this level sets of this elliptic curve for various, for t is non-zero, will somehow look like this. So what you have here is again, if for t is small, you have the picture, sort of deformed picture of what we had, which I was discussing there. And now the idea of Crystal is just find a map, mapping this to that. So what you do is the following. You write the equation in the following form. So just expand this. So you get here something and here t times something. And then you solve for t, I squared. Now what you see is that, you see in the neighborhood of the singularity, you have sort of the curve as two components, but they're curved. The equation of this curve is irreducible. You cannot factor this. You cannot factor this polynomial. But in the Henselization of the ring, you can do the factorization. If you allow square roots, you can factor this as u times v, where u is vanishing on the one branch and v on the other branch, and this you can just do u is 1 plus x. You just factor this expression is y min minus x times the square root, and then you have to divide by the square root of, and then times v is minus. So these are sort of two, this maps the nonlinear equation here to sort of the linear, the hyperbola equation u times v equals t. And now you look at the differential form we were wanting to take the period of. So it can be expressed in x and y, because dx over y is the square root of this whole thing. So this is our form omega, but now you have a coordinate transformation from x, y to uv. So you can express this in uv. And then the result is that can be represented as the square root of 1 minus u. So this is a calculation which you can do, but it's not easy to do it by hand, but Crystal does it and say, if you express it in this coordinate, the result is this. Hence, the integral of omega, so this is our period function, is going to be the diagonal of this function. And now, if you're unsure, the best thing to do is go to Maple and take this function, expand it in this power series, and look up the terms on the diagonal, and you will see that it is indeed f half t. Precisely. So Cristol has a sort of method to write a period, because the period we were looking at, the period function phi t, was dx y. And we integrate over vanishing cycle. It's contracted. And here, you can rewrite it in this way. You get du over u, and then it's the diagonal of this, two diagonal of this algebraic function. So the algebraic function comes in here because of this coordinate transformation cannot be done over the rational, with rational functions. You need square roots. You need algebraic functions. So it's in the étale topology. This singularity is curved singularity. This is in the étale topology, so up to a coordinate transformation, is the standard hyperbola, as we had before. So the period you're computing is a period over a very small cycle, and here it becomes a cycle here. It becomes the expression for the integral which defines the diagonal. So it's just a coordinate transformation. So how does it work now in general? It was a long story which I'm now going to cut because of the time. So if you now have a d-dimensional variety, and it gets, and you have a point of maximal unipotent monodromy. So you have a maximum number of logs. It means that in the variety, after blowing up a resolution, you get that so for d is 1, we have this crystal picture. And d is 2. If you have a family of surfaces, then having a maximal Jordan block means that you're going to have in the intersection of your divisors, you will get 3 surfaces intersecting. And there is a torus integral here going on. So here you have x, y equal t. Here we get x, y, z equal t. Everything generalizes. The method of computing a diagonal is now integration over a three-dimensional, over a two-dimensional hyperbola with this equation. And now having a maximal Jordan block means that in the resolution you need to have 3 surfaces coming together. Therefore, the period integral is concentrated to an integral over a torus. And this writes then if you add algebraic functions, you get a representation of your period function as a diagonal of a function in d+1 variables, algebraic, and therefore rational in double the number of variables. That's the reason. So I think this is a particularly beautiful idea, a very fortunate idea of Cristol. And yeah, so André was very modest about this extension to higher dimensions. He says, well, it's really there. So I think I stop here because of the time.